Should I record it?
Yeah, I have started.
Okay. So, hi everyone. My name is Michael, and today I'm going to talk about the mathematical foundations for deep generative models, right? And it's a really important part for all generative models research. And today, the math foundations is most about the linear algebra and the probability theory behind it. It will not be very hard, but you can see some very good insights for them. And it's mainly about the deep generative models, but not the traditional machine learning generative models that you have might see as the hidden Markov or something like that. So which means the generative models today I'm going to talk about is to use a neural network to train. Okay, and yeah, I have put the slides on the GitHub, and you can access the slides here. Okay, so the first one is for the ultimate goal for the generative models. We know we have to train a model that can make it generate new samples based on the given data input. So our ultimate goal should be find the optimized parameters for our neural network that can minimize the kind of distance between the real data distribution with the data distribution that our model represent, right? And you can see here, this D in this formula is a measure of distance. And if you have already know some of the theory for generative models, you may know it's kind of divergence, right? There's multiple ways of writing divergence. For example, the divergence or GIS divergence. They are measuring the difference or how far we can go to move one probability distribution to another. But what I want to say here is that it is not really a distance metric because this distance metric requires lots of conditions and they're not very good to meet the requirements. But the square root of JS divergence is actually the only distance metric. So for P of theta, you can see here it's a model parameterized by theta, and it's a neural network in deep generative models. And the model for P, we means it's a probability density function for the data distribution. And for P of theta, it's a real data distribution in terms of probability density function or PDF. So one question is, do we really have the real PDF for the data? We do not because you know probability density function is a continuous number of training samples. So this is the problem about the discrete versus the continuous. And we are only given the limited sample data, right? I write it as this. Right, so we can see here that we are only given a set of data that is written as the set A here, and it contains capital N numbers of samples from X1 to Xn, and each of them of Xi is in the R of D, so which means our model dimension is D. And in the next slides, if I write down R of D, it means that our model dimension is D. Okay, so each of them are assumed to be independently and identically distributed from the data distribution. This is the real data distribution, and this is the limited samples we can get from it. and they are assumed to be independent and identically distributed from it. So from these samples, we can define the empirical distribution for estimating real distribution. So this is a discrete one, or a probability mass function, which is defined as for every position, if it is in the data set, we write it as one, otherwise it's zero. And because we have capital N numbers of samples, so we will have a coefficient of 1 over capital N, so that when we do this sum overall samples, we can get 1 to ensure that it is a probability mass function. And we can also use delta function for writing down the discrete empirical data distribution. And also we can use this formula to get the expectation of any function f of x with respect to this empirical distribution of data. It's just the summing over of all function values that the input is our xi. Okay. So next question is how to define those measured, how to measure the divergence or the capital D that is in the ultimate goal, right? So the most common one is KL divergence. It's originated by information theory. So if we have an information X, it can be like an image or a text, and we want to encode it with a data distribution P. And it is proved that the optimal bit size for encoding X is the negative log value of P of X. Right, so this is take the X as input for the probability density function for all of the data distribution, right? And we take the negative log function out of it. So this is intuitively correct as well, because we can know if the information is more common, then the bit size we need to encode it should be less, and vice versa. So hence we can define the information entropy for P, and it's written as H of P, which is the expectation of choosing any X out of their data distribution P, and the expectation is taken on their I of X, right? This is just I of X. Okay, so because it's an expectation, we can expand it as the integration so that the later calculation is more simple. And also we have a cross entropy if we use Q to encode P. So P, what is P? P is the real data distribution of X. So we can use another probability distribution Q to encode P. And this cross entropy, you can see it is just the expectation taken on X over the real distribution P, and the function is negative log Q, right? And this is just the expectation taken over P of their bit size, right, of X under Q, right? This is because when we taken out our samples X from the distribution P, and we use Q to encode that. So we draw from P and we use Q to encode that and take the expectation, which is the cross entropy if we use Q to encode P. So here we can calculate by doing the difference between them to know how many bits are wasted if we use Q to encode P, right? So it's just a difference between HP of Q, which is the cross entropy, and the original entropy. And you can see it results in this function, right? So lots of divergence function is on the form of T log T. And the KL divergence is one. It is called the family of F divergence, which contains the term T log T. You can see the T here is Px, and it can, maybe we can write another symbol because it's P over Q. And you can see here, if we write down it as expectation, it's still we draw from P the expectation of log Q over P, right? So this is the most common divergence that we can make, which is the KL divergence. So intuitively, we know that KL divergence must be greater or equal than 0 because we used Q to encode original P, which means the Q is not the optimal encoding for all of the X. So there are some amount of information will be wasted, right? So the KL divergence of between P and Q, okay, so this is important because the KL divergence to use Q to encode P uh, is not equal to the KL divergence of Q. Use P encode Q, right? This is also intuitive true because if like P is covered by Q, then one of them is very big and the other should be very small. So we can use math here to see that the KL divergence, if we use Q to encode P, is greater or equal than 0. And what we use here is to use the Jensen's inequality, right? We know it is a convex function for log function, right? So we know that for Jensen's the convex function phi taken on the expectation of x is always less or equal than we take the expectation first and then take the function y, function phi, right? So here you can see because we move log out of the expectation function, remember this integration over p is the expectation, right? And also we have a negative sign out of it, so we flip the sign of the inequality and the p cancel out, which leaves q. And recall that q is a probability density function, which means if we integrate it over the domain, then the value should be 1, right? So it just negative log 1, which is 0. So we have proven mathematically that the KL divergence is never negative. But can we find an upper bound for the KL divergence? No, because when we take qx is 0 or the limit of q is 0 at some point, then since q is work as the uh, denominator here, which means our KL divergence will finally converge to infinity, and it may cause the problem of exploding gradients. So for the solution for that, we can introduce a new one called the JS divergence, right? The core idea is to find a middle distribution between P and Q, right? For example, we have P and Q, and we can find some middle distribution M, and to measure the distance between P and M and Q and M, and do an average between them as the final divergence between P and Q. Right, so mathematically speaking, we are first finding the average function m of x as the half of p plus q. Then we can define as their average of if we use m to encode p and we use m to encode q, what's the total divergence, right? Because there is two terms, so we just simply do 1/2 of the coefficient. So it has a very good nature that it is symmetric, right? Because if you want to swap Q and P, you can easily see from this formula that they're the same. The second is the lower bound. Since all of the KL divergence is greater or equal than 0, so JS divergence as the sum of two KL divergence is also never negative. And also for the upper bound, okay, so let's see from the upper bound here. We can first calculate the upper bound of KL divergence if we use M to encode P. So why here it will not explode to infinity is because M is the average value of P and Q, right? So it will cover some point between P and Q, which means the M now will never be at 0 some point if we assume P is never 0, since we want P is the optimal one of all distribution. It should be continuous and with a very good shape of the probability density function. And here you can see it's take the integrate of P of log P over M, where M is half of P plus Q. So we can take the half to here, right? And we can divide P on the inner part of the log function, right? Because we assume P is never be zero. And what this 1 over 1 plus Q over P is less or equal than 1 over 1 plus 0, right? So this is just 1. This should be equal sign. Okay, so the log function is less or equal than log 2. And we can take the constant part log 2 out of the integration. And what left is the integration of px over all of the x. And it's a probability density function, which means it's 1. So it results in log 2. And now JS divergence is the total sum over 2. So we got 2 copies of log 2 and divide by 2. So we got the upper bound for JS divergence is log 2. Okay. So after talking about the divergence, we are there is another important things called the maximum likelihood estimation, or the MLE, right? It's the core idea of all the training process for generative models. So we can back to the training data A that is from x1 to xn, and write down their joint probability for appearing in P of theta, right? So we have a probability function that we use the model try to fit, which is P of theta, and we hope all of the training samples have a maximum probability for appearing together in P of theta, right? This means that we have find a good fit for P of theta. So since we know x of I are independently and identically distributed from the original P of theta, and it should be also independently in the P of theta. So their joint probability can be written as a product of all of them in P of theta, right? And if we want to maximize this probability, it has a product sign, right? We can use the log function to convert this product to a sum over all of the samples, right? So the argmax of the product of their probability is equal to the argmax of the sum of all log probability of the samples. So remember that for the empirical or discrete versus continuous slide, we can transform this sum of functions to the expectation when x is drawn from the empirical distribution. And the thing we want to find the expectation is the log probability. So now this gives us the MLE best parameter set theta is just to argmax the expectation of log probability. And actually, it has very big relationship with the KR divergence as well. So we can first write down the KR divergence in terms of empirical distribution, right? Because since it's original, something like this, right? And now we use the empirical distribution to substitute this P and to use our P of theta, that is our model distribution, as Q, right? And because they are discrete, so we use a sum rather than the integration. So we can write down the sum as Pn log Pn over P of theta, and we expand it. So the first term, you should know it is just the information entropy of the empirical distribution. And this is the second term. We can leave it now. So to see later how we can transform it. So therefore, for the optimized parameter theta on KI divergence, if we want to minimize their distance between the real distribution from the probability distribution that we use the model to fit, we are just doing the argmin of the KL divergence using P of theta to encode P of theta, right? So by the result on the last slide, it's the entropy minus this sum over P log P of theta. And the information entropy of the real discrete sample empirical distribution is a constant because it is what we already have and do not involve any variables. So it's a constant, we can discard it. And because the later term, it has a negative sign, we are just doing the argmax of the positive part of it, just the argmax of the sum of P and log P theta, right? And this is just the expectation of all x's drawn from the empirical distribution, and the function is log P of theta, right? And this is exactly we have got from the MLE method, right? So we can see from here that if we want to maximize the likelihood or to use the MLE method, we are actually doing to minimize their KL divergence between the empirical distribution versus the our P of theta distribution. And also notice that if we convert all of the sum sign to an integration, we can know that it is true when P of theta is actually those theoretical continuous distribution. It should not result in any change here. So for the next step, we have finished some basic knowledge check for basic divergence and the MLE method. So we can back to the first slide. Remember that we should build a model of P theta x and to minimize their divergence, or we can say it's to maximize their log likelihood on the P of theta. So how can we actually build a model of P theta of x? There are some known approaches. The first is the most simple one, right? We can explicitly write down P theta of x, which is the autoregressive model. We can also use the implicitly get P of theta, that is to use the latent space, or use a prior distribution Z that is from P of Z, which is a prior distribution, right? We use that to help us write down P theta of x. Or we can just learn a function about P theta of x, which is the score model. We learn the gradient of P theta of x, right? As the score, and to learn which direction should the sample go when we are sampling from it. So start with the most simple one, the autoregressive model. For every sample X in the data space, it's D dimension. So we can write out its component as X1 to X of D. So we know that by probability decomposition, the probability of X that appears is equivalent to X1 first appears, and its probability times the probability of X1 has already been seen, and what's the probability of X2 to appear. And then we continue to do this process all the way to if X1 to XD minus 1 has been drawn out, what's the probability of XD to appear? All right, so this is P of X, which is a product of all of P theta of xt, given that all the component that is less than t has been seen, right? And here we use P of theta means that we put it in our model instead of the real data distribution. So still we follow the idea of MLE, right? We want to maximize this sum over the log likelihood of P theta xi, right? So this xi is not the component, it's one sample, right? Remember that set A, right? So we want to maximize the sum of all log probability of the samples. We can expand it, so we maximize summing over all samples and summing over all steps to take the log probability of xti, given that the sample xi has the t minus 1 component being drawn, right? And that is the autoregressive model. So back to here, we know that it is the explicitly write down of P theta of x. So we got a term that we can optimize on. And also we can implicitly get P theta of x, which is the next model I'm going to show. It's called the normalizing flow. So now we can also introduce a simple distribution. This is also called the Prior distribution Z, that is in PZ of Z, right? For example, it could be a normal distribution in high dimension, right? In the latent space R of D. And why the dimension is due equal to the model dimension is because we hope this F is a bijection, right? So being a bijective function means that the dimension of the two, the domain and also the codomain should be the same. So the Prior distribution should also be in R of D. And this bijective function is f of theta. So you can see here, we originally want a bijective function f from z to x that we can map every point on the Prior distribution to the real data distribution. But how can we get that f? We can use a neural network to train and to get that function, right? Because the neural network has the universal approximation theorem. So here, back to this normalizing flow, we will use the f of theta to train that it push forward the distribution of the Prior Z to the data distribution Px. And following is some math from it. So the first one is the change of variable function, because it's in a higher dimension, and we know the change of variable should have a coefficient of the absolute value of the Jacobian determinant, which is the determinant of the partial f over all partial x, right? So we can write down as dx equal to the Jacobian times dz. And also, we have another thing that is the probability conservation. In the process of push forward, we push from a simple distribution PFC to a complicated one, the real data distribution. We hope the probability should be conserved. That is, the probability density over a small region should not change, right? So the density over a small region in the P of x should be P of x times dx, right? Because P of x is the probability value and the dx is the little region we're finding the probability density. And also the other side should be Pz of z times dz, right? And we know Pz of z times dz, we have dz is dx over the Jacobian determinant by the change of a variable. So we can get this formula. So we can keep going on because we know f is bijection, and the inverse of f composed with the original f taken on any Prior z should be the identical function taken on z. It should not have any change, right? So by the chain rule, if we take the partial derivative for the right-hand side, it's an identical function, so it should not change. And for the left-hand side, we can we are doing the partial of f inverse over x first, and then doing the partial over z. So we know the partial of f over partial of z, and its whole inverse is equivalent to the partial f inverse over partial x. So from here, this PZZ determinant of f over partial z inverse, we can transform it as PZ of z times determinant of partial f inverse over partial x. And the dx term is canceled out. So our final result should be p theta of x. Now we use the we plug it back to the model p of theta, right? So p of theta should be defined on our parameterized function f of theta, and it's defined as the first we take the f theta inverse to the Prior distribution p of z and times the determinant of f inverse over partial x, right? So this is also intuitively right? Because we draw from the Prior distribution, we go by a volume correction term that we times its Jacobian determinant to get the final p theta of x, right? So here we use the Prior z to implicitly write down p theta of x. And it follows that we want to also, by the method of MLE, to maximize this log likelihood. And it's the argmax of, if we take log, then the two terms will separate. So the first term is PZ of F theta inverse plus the log value of the inverse of Jacobian determinant. And you can see from here, it's actually two terms. The first is the base log density, and the second is volume correction as the optimizing goal for the model, right? So this is the whole structure of normalizing flow, the theoretical background of it. So we can see that we can use the prior distribution Z to implicitly express out what is the log likelihood of P of theta, right? But there is a problem, right? Because we know to find a bijective function and also compute its Jacobian determinant is not easy, right? It is not easy and also very costly in the real process of computing a Jacobian determinant. So we can try to find another approach that is simpler, right? So we can know that there is another model that is very similar to it, which is the generative adversarial network, the GAN model, right? So in normalizing flow, F has to be bijective and it requires a tractable Jacobian determinant. Oh, sorry, this is syntax error on latex. Ignore it. And on the generative adversarial network, we can still assume we have a simple distribution. The prior distribution Z follows PC of Z in the latent space R of K. Right now, because we do not require it to be bijective anymore, the dimension can be K less than D, right? It is not required to be the same. So we can still define the generator G of theta. We call it G of theta, but we can think of it's another F of theta as in normalizing flow because we want to move every point C on the prior distribution to the real data X, right? So we go through the function G of theta of Z to get X. And G is not necessarily bijective. But the problem now becomes that we are unable to write down the in very good expression for the log likelihood and perform the MLE to max to make the parameters in the optimal situations, right? So the solution is to add a discriminator as the supervising signal for it, right? And here, we have the value function of V, D, and G. It's composed by two of the components, D of theta and G of phi, right? It's defined as the sum of the two parts. The first term is the expectation when X is drawn from the empirical distribution and take on the log value of the discriminator function D of X, and plus the expectation when X follows our model distribution P of theta times over the log function of 1 minus D of X, right? And because D is always 0 or 1, so we know the two-part expectation taken over by log function, it's either log 0 plus log 1 or log 1 plus log 0, and it's never positive. But we can see that if X is in P of n, the generator wants a score of 1 on P of theta, right? But the discriminator wants a score of 1 on the real data, but 0 on P of theta, because P of theta is given the output by generator, which should be a fake result, right? So we have this, right? For generator, when P of n, the dx value is 0, it's log 0, right? Plus when X is from theta, it should be 1, so it's still log 0, right? It's negative infinity for G. So G wants it to be negative infinity, and D wants it to be log 1 plus log 1, right? It should be 0. So we can see from this value function, the discriminator is trying to maximize it, but the generator is trying to minimize it. this giving us the zero-sum game that the DS want to maximize the value function, where G generator wants to minimize zero value function. So our goal here is to find out, given that the discriminator is very good in distinguishing that, how can we find the optimized generator that can make its fake output more similar to the real one? And first step is to find how can we define that our discriminator is optimized, right? Here we first let the generator to be a fixed value, so we can write down its value function that is only dependent on d. It's p of n times log d plus p of theta times log 1 minus d. Since we want it to be optimized, we should find the point where the derivative of it should be zero, right? So we calculate the differentiated f over d and let it to be zero. Remember, the derivative of log function is just 1 over the inner part, right? And solve this function, we got the optimized d should be p of n over p of n plus p of theta, where p of n is the empirical distribution and p of theta is the model distribution. So here, I think you have already been discovered that this is 2 times m of x, right? In JS divergence, we know we have taken out the average function of two distribution. So this should be related to JS divergence, and you can see in this slide, we can find the optimal G given the optimal D. We first denote M to be half Pn plus P theta. Then we have the value function of G given the D is already optimized to be the two-part expectation sum. The first one is log P over M, and we get a half and 2. This is just we want a coefficient that correspond to JS divergence, right? But we have also a 2 on the denominator. So because it's a log function, we can minus it out. We can minus log 2 here and also minus the log 2 here. So we result in minus 2 copies of log 2. And the front, it's a half of 2 expectation of log value of the distribution over their average distribution, which is just a JS divergence between the real distribution and the model distribution, right? And this is a constant term, so we can discard it when we finding the optimal parameters. So what we are doing for parameters is just the optimized theta is the arc mean value of JS divergence for using p theta to encode p of n. And it is equivalent to minimize the value function of d and g given that d is in the optimal situation, right? So this is the GAN model. We can see it's still, we use a prior distribution and we try to find a map from the prior to the real data distribution. And because we cannot get the PDF written down, so we use a discriminator to provide signal for optimizing the generator or the mapping function. And right, there is also very similar model that use the same idea. We still have a latent space or prior distribution, and we are exploring ideas from using a functional mapping from the point on prior to another point on the real data distribution. But how about we have a map from the point to a distribution, right? That is the variational autoencoder. So still we have the simple distribution that is maybe a normal distribution defined as Z follows PZ of Z in the latent space R of K. We can find its output in the real data distribution as one distribution, P theta given by Z, the value of X, right? So we can draw it. For example, this is the real data distribution. And we have a regular one, which is the prior, right? So if we sample a Z from the regular distribution, we can map to another distribution under P of theta. right? And all of the point map to different different distribution, right? And the summing over all distribution, we want to minimize the summing of all distribution with the real data distribution. So this is what we are doing using this formula, right? All of the distributions given out by the output should be the sum over all P of Z if we draw Z from the prior distribution and we times their distribution over here because it's a marginalization process, right? And if we summing over all of them, we are doing the summing all of the distribution here to get the P of theta, and we want to minimize the distance between P of theta and P of theta. So we can write down P of theta as well using marginalization, use the prior distribution. And the problem is Z is continuous in high dimensional space. We don't want to integrate over such a variable. So what's the solution for make it simpler? So we have a following trick about the evidence lower bound. We can introduce another distribution that is the posterior distribution that is learned by our another network Q of phi, right? Of x given the z given by x, right? It's saying that we have the data distribution x and we take a value x of it, we should map it to a distribution. And if we have lots of x mapped together, the summing over should be the original prior distribution, right? So the log likelihood of P of theta is the log of the integrate of Q phi z given by x times P theta of the joint distribution of x and z over Q phi, right? Why we are doing this? Because we want to perform the Jensen's inequality so we can transform it to a better expression, which is the evidence lower bound, right? We still perform Jensen's here, right? To get its integrate of Q phi of z given by x times the log value of P theta x by given z times PZ over Q phi z given by x, right? So this term is defined as the evidence lower bound. Why it is a lower bound? Because we know our log likelihood is always greater or equal than this lower bound. So in the process of maximizing our log likelihood, we can just doing to maximize our evidence lower bound. If the lower bound is as high as possible, then we can to maximize the log value of P, right? So we know evidence lower bound can be written as the expectation of log P theta minus log Q phi minus log PZ. And the second term is the KR divergence of Q phi if we use PZ to encode it, right? If you still remember KR divergence, it's P of log B over Q. So we can see we have Z here, so we times the Q phi Z over X times the log Q phi over P, which result in the KL divergence of using P to encode Q of phi, right? And the first term is keep the same as this expectation of Z follow Q phi of log P theta of Z given by X given by Z. So we want to maximize log likelihood is equivalent to maximize the evidence lower bound. And we know it's find the maximum value of parameters that find the parameters that can maximize the function of expectation of log P theta z x given by z minus their KL divergence. So this is similar in the normalizing flow, right? In normalizing flow, we have an objective. The first term is the base log density, and the second term is the volume correction. And here we are still use the decomposition of two parts. The first one is the base log density, right? From given NZ, we want to reconstruct the data of X. So what's the expectation of the log probability? If we can maximize it, we maximize the base log density, right? Because we want to our mapping to reconstruct the data sample. And the second term is a posterior correction. We want from given an x, we go back to find the original prior z. We wanted to be minimize their distance from QFI to the real PZ. So the second term, it's a minus sign. We are actually minimizing the KR divergence of the posterior with the actual prior. So this is the variational autoencoder, which also use the idea of use a latent variable z to write down the expression of P of theta. Oh. Also, I think, yeah, if it is too long, I can end up here. But is there any other time for me, or I should end up here?
Yeah, I think we ran out of time. So anyone has any question about Michael's lecture? Okay, yeah. So this is a great lecture because the one key message we want to send to all of you is that so for doing artificial intelligence, actually, math background is very, very important. It's very crucial because for many AI models, so they are built on top of some mathematical reasonings. So that's very, very important. You can't just say do everything in a black box without knowing what happens inside it. So that is not the right way to do artificial intelligence. Yeah. And also another thing is, so sometimes when you try to learn some new AI models, in particular, because this field is developing so fast, so we have to read lots of original papers. But many papers were written in a very mathematical way. So you couldn't understand the math reasonings behind those AI models. So once you see the new AI model, and when you even try to replicate the model, so you couldn't even understand how it works. You couldn't even understand the paper. Yeah. Any other question?
Yeah, if you can, you want to see the later part about score-based model and the relation between the DDPM, you can access the whole slides here on the on this GitHub link. Right. Okay. Thank you.
Yeah. All right. Thank you so much, Michael.